Boyle's law is a gas law discovered by Robert Boyle which relates the variables of volume and pressure. So before I begin on Boyle's law, I'll give you some background on the man who discovered it. Robert Boyle was born in Ireland in 1627 and was the 14th child of one of the wealthiest British families at the time. Boyle was an Anglo-Irish natural philosopher and theological writer best known in the field of chemistry. Being an extremely religious person, Boyle's main studies over his lifetime were surrounding the relationship between science and religion, as he tried to prove that they were mutually supportive. Boyle was advanced for his time, which was extremely superstitious, as he believed that principles and methods of chemistry and science in general should be applied to the natural world and advancing medicine. Boyle has later been referred to as the father of chemistry. Robert Boyle had some major achievements in science which not only included the gas laws. Some of these were that he established that electrical forces are transmitted through a vacuum, but that sound is not. He stated that the movement of particles is responsible for heat, and he was the first person to write specific experimental guidance for other scientists, portraying the importance of reliable and repeatable results. These achievements and his discovery of Boyle's law caused huge advancements in scientific discovery. Boyle was the first person to discover a gas law, and he made this discovery in 1662. There was some dispute over the discovery of the law, as it was also called Marriott's law, after a French physicist, Edme Marriott, who also proved the law, but in 1676. Boyle's law is a relation describing the compression and expansion of a gas at a constant temperature. To describe this, the variables which are affecting it and being affected are volume and pressure. The law states that the pressure of a given quantity of gas varies inversely with its volume at a constant. The product of the pressure and volume are observed to be nearly constant for an ideal gas. It is important to remember that this relationship is accurate when temperature and mass are constant. So to describe this relationship, we can use two equations. The first one is PV equals K, where P equals pressure, V equals volume, and K is a constant. This means that the product of pressure and volume is always equal to a constant. If we increase one, the other decreases. And if we decrease one, the other increases. This can be called an inverse relationship. You can also use the equation P1V1 equals P2V2. This is generally used in calculations to find a certain variable after making a change to another variable. These two diagrams clearly portray this relationship. Looking at the one on the left, the mass and temperature are held constant. As the pressure increases, the volume decreases. Or it could be stated that as the volume decreases, the pressure increases. The diagram on the right shows the volume decreasing and therefore the pressure increasing. Keeping the other variables constant is very important. In Boyle's law, the temperature must be kept constant, as temperature and volume have a direct relationship, stated in Charles's law. This means that a change in temperature would also change the volume, which is what we are comparing, and would make Boyle's law inaccurate. This is also true when keeping mass equal, as it affects the other variables. When following gas laws, we must think about which variables are kept constant, as the variables of pressure, volume, mass, and temperature in a gas are all related in some way. Boyle's law was discovered following the invention of the vacuum pump. So the vacuum pump was invented in 1654 by scientist scientist called Otto van Guericke. It can be seen in the image on the slide. That is the vacuum pump that he invented originally. Robert Hooke improved upon the model of the vacuum pump. So when Boyle learned of this invention, he discussed the concept with Hooke. Boyle and Hooke carried out experiments to investigate the properties of air and the vacuum, leading them to discover Boyle's law. So the experiment Boyle used to discover Boyle's law was established from the theories he discovered while observing the vacuum pump. Boyle used a glass J tube called a manometer. This can be seen in the picture on the slide. Inside the manometer, he used different volumes of mercury liquid to vary the pressure on a fixed mass of air at the end of the tube, which is sealed off. So the end of the tube that you can see is sealed off. He put the same mass of air in several different tubes so they were consistent, and then he put different volumes of mercury in to change the pressure, increase it and decrease it. And through studying this, Boyle discovered that pressure multiplied by volume is always a constant. So on this slide, you can see the graph of the real results of Boyle's experiment. This experiment proves that when you increase the pressure of a gas, the gas's volume shrinks in a way which can be predicted. It's important to note that this relationship is inverse, meaning the graph would generally go from the top left corner to the bottom right. But in this graph, the reciprocal volume is used to highlight the relationship. So it's not a direct relationship as it looks in the graph, it's actually an inverse relationship. Now I'm going to go through some real life examples of Boyle's law. So the first example I think of when I think of Boyle's law is your ears popping with change in altitude. So if we're in an airplane landing or driving down a mountain, the altitude is going to change. It's going to get lower. And as the altitude gets lower, the pressure increases. Now, from Boyle's law, we know that if our pressure increases due to the inverse relationship, volume must decrease. So the pressure increases as our altitude decreases. Therefore, our volume is going to get decreased, and the volume in your ear is actually going to reduce. As the volume in your ear reduces, this air actually has to escape so they can equalize. And the air escaping through the ear canal is what causes the popping. The opposite effect is if we are increasing in altitude, we're going up in an airplane or driving up a mountain, your ears are going to hurt. This is because the pressure's decreasing, therefore the volume is going to increase, and this volume increasing within your ear canal causes pain. We actually have a valve in our ear which equalizes this, minimizing these pains and popping to keep in line with the change in pressure and stop it from causing harm. Another example of Boyle's law in real life is pushing on a balloon. If we push on a balloon, it's going to decrease the volume of a balloon and therefore increase the pressure. If you keep pushing to a point that the volume is decreased so much that the pressure gets so high, it will eventually burst. Another example relating to a plane again is if you take a chip packet on a plane. When you increase the altitude you go up, the pressure of the air is going to decrease. Therefore, the volume is going to increase, and this can cause a chip packet to explode. Now I'm going to go through some worked examples of Boyle's law. So my first one is about a helium balloon. So a helium balloon we have has a volume of 796 milliliters at ground level. The balloon is then moved to an elevation of 6 kilometers, so it goes up 6 kilometers in the air, and there the pressure is 0.47 atm. At this altitude, the gas or the gas in the balloon now has a volume of 1012 milliliters. If the temperature is constant throughout this, or what was the ground level pressure? So our volume has increased as we went up that elevation from 796 to 1012, and we've got our final pressure value. We just need to find that initial pressure. So you can see this in my working. I've seen that the initial volume was 796 milliliters. Our initial pressure is what we need to find. It's unknown. Our final volume was 1012 milliliters, and our final pressure was 0.47 atm. So we can calculate this initial pressure of the gas using the Boyle's law equation. P1 V1 equals P2 V2. So we sub our values in, and on one side we have 0.47 times 1012, and we're actually just going to simplify that to 475.64. We then need to get our unknown value by itself, so we're going to divide through by 796. This is 475.64 divided by 796, and this is going to leave us with P1 equaling 0.60 or zero point 0.6 atm. Therefore, the pressure at ground level initially is going to be 0.6 atm. Now we're going to go on to our second example. So, a gas exerts a pressure of 2.9 kPa on the walls of a container, which we're going to call container 1. So, we're going to empty container 1 into a 14-litre container. And once this has happened, the pressure exerted by the gas increases to 8.6 kPa. If the temperature and the amount of gas stay the same, what is the volume of container 1? So, we have our constant variables of temperature and mass staying constant, and we have our two values for pressure and our final value for volume. We're trying to find that initial volume. So we're going to go into our working. We identify our values. Initial volume, we don't know. Initial pressure was 2.9. Final volume was 14 liters because we tipped into the 14-liter container. And final pressure is 8.6 kPa. So we can now calculate this using the same equation we did in our last question. We sub in our values, and again, we're going to go 8.6 times 14. This time is 120.4. We then got to get our unknown variable by itself, so we're dividing through by 2.9. 120.4 divided by 2.9 is 41.52, which we can simplify to 41.5 litres. Hence, the original container's volume is approximately 41.5 litres. Thank you for listening.